This video is about the transformation of rotations. Rotations, another word for rotation is a turn. Rotations will change position. There is a change in position. So as you rotate it, as you turn something, it will actually move its location, so it does turn. Rotations have a change in orientation. So as you turn something, it's going to be pointing in a different direction, so it will change in orientation. As you turn something, it will stay the same size and the same shape, so the figures, again, are isometric. That means that they are congruent. The pre-image and image are congruent. Now, a couple of things about rotation. First thing is that rotations do have a center of rotation. It's a center or a point of rotation. And we will actually call that R for future reference. R. Generally, it's going to be the origin, but it does not have to be. There is a way you can change it to where it's not the origin. But all of the rules that are used here, all the mapping rules and the description, are based off of if the center is the origin at 0, 0. The other thing we have to remember about rotations is that in order to rotate, it needs to go counterclockwise. Counterclockwise. The reason we do this is because of the order of the quadrants. They go in, if we have X and Y, quadrant 1 is up the top right, then quadrant 2 is the top left, 3, and then 4. They go in order from right to left and goes in a C. So quadrants 1, 2, 3, 4 is why we go counterclockwise. Now to rotate, because we're going to be doing it in a coordinate plane, we're actually going to be dealing with four very specific rotations, 4 very specific degrees. We're not going to be doing any weird degrees, but very easy to see. It's going to be the 90 degrees. It's going to be multiples of 90. So it's going to be 90, 180, 270, and then back to 360. 360 degrees actually puts it back to the original. So the words, the description is our words. This is to rotate this many degrees. So to rotate, we're going to deal with 90 degrees. We're also going to deal with 180 degrees, 270 degrees, and 360 degrees. So again, we're going to focus on the words, and then we can build our mapping rules from the words. So for 90 degrees, to rotate 90 degrees, that goes from quadrant 1 to quadrant 2, or 2 to 3, 3 to 4, 4 to 1. It just goes one quadrant over. You will flip, and this order is important that you do this. You flip the X and Y's, then you negate the front number. You negate the front number. It's important that you know which one to do. 90 degrees comes first, so you're going to negate the front number because it's the first part of the coordinate. 180 degrees is the next one. We're going to rotate 180 degrees, which actually moves it 2 quadrants. So it would go from 1 to quadrant 3. It just moves 2 quadrants. So wherever you're at, move 2 quadrants counterclockwise, and that's 180 degrees. As long as you're careful on your coordinates. 180 degrees, you're not going to flip anything. You're just going to negate. You're actually going to negate both the X and the Y values. So you negate the first or the front number, then you negate both of the numbers. For 270, 90 and 270 are very similar to each other. If you think about a clock, 90 degrees would go from 12 counterclockwise to 9. And then 270 degrees would go from 12 all the way to 3, which are across from each other. So they're going to be very similar to the 90. So we are going to flip the X's and Y's. Flip x and y's. Then negate the the back number. Negate the back number. It's hard to see that. Back number. So the first one, we negated the front. Then we negated, so it went first, then 1 and 2, and then just 2. So we went first, both, and then the last. For 360 degrees, you actually have no change because it goes right back to the original. So if we look back at the quadrants, 90 degrees will move 1 quadrant, 180 will move 2 quadrants, 270 will move 3 quadrants, and then 360 will move 4 quadrants, which puts you right back to the original. Now, sometimes the problems won't say to rotate counterclockwise. If it just says rotate, that is automatically counterclockwise. But sometimes problems will say to rotate clockwise. That you have to change. So if it says to rotate clockwise, we need to do the counterclockwise equivalent. So do the counter equivalent. So we need to think about which ones we need to do the equivalent of. If we think about, again, about a clock, 12, 3, 6, and 9. So these are the easiest ones to look at for 90, 100, 270, and 360 degrees. So counterclockwise. If we want to go counterclockwise 90 degrees, that would go from 12 to 9. I need to know how many we need to go clockwise, again, to get from 12 to 9. So 12 to 9 is 90 degrees counterclockwise, but then 12 to 9 clockwise is 1, 2, 3 times around. So that is 270. That's clockwise. If we do 12 to 6 counterclockwise, that is 180 degrees. From 12 to 6 is also 180 degrees clockwise. So there is no counter equivalent for 180 degrees because it's going to be the same. If counterclockwise from 12 to 3 would be 270 degrees because it moved 3 times. So from 12 to 3 clockwise would just go once, that'd be 90 degrees. So the 90 and the 270 for both actually were opposites of each other. But the 180 didn't have to do anything. You didn't have to do a counter for it. So 360 counterclockwise has to go all the way around. Clockwise does the same thing. So that means that 180 and 360 are actually the same for both clockwise and counterclockwise, but the 90 and 270 are not. So if you see you want to rotate 90 degrees clockwise, you are actually supposed to do 270 degrees counterclockwise. You need to follow that rule instead. If it says to do 270 degrees clockwise, that means that you really want to do the 90 degrees counterclockwise. So you'll do that rule instead. But the 180 and the 360 actually follow the same rule because it will go to the same location, regardless of clockwise or counterclockwise. The 90 and 270 don't. For the algebraic, we're going to talk about the mapping rule. So this is the rule. If it asks for the rule, you write out the mapping rule. So we're still going to talk about the 4. We have 90 degrees, 180 degrees, 270 degrees, and 360 degrees. So we're going to start with our pre-image, our x, y. 90 degrees, if we go back to what it said to flip them and then negate the front number. So if we flip them, it's going to be y comma x. And we want to negate the front number, which is right here. We want to change this sign. So it'll be negative yx. For 180 degrees, we start with a pre-image. Maps to, and the word said to negate the x and y values. It just said to negate them. So we change both of the signs. So we become a negative x and a negative y. For 270 degrees, again, we have our pre-image, maps to. The word said to flip them, then negate the back number. So we're going to flip them, so it'll be y and x, then negate the back number. Now the back number is right here. We're going to change this sign. And then 360, again, our pre-image, x, y, maps to. They said no change. So my x is going to stay x and my y is going to stay y. There's no change. Now, as you can see, as I was talking about earlier about the negative signs, if you look at these, the first one is negative, then both are negative, then the back is negative. So it actually goes in, as it rotates in, you can see a negative, then both negatives, then your negatives are actually starting to rotate out until there are no negatives. Now it's kind of weird to understand. If I do it like this, I can say that my pins are my negatives. So right now they're not inside of them. So then as I go 90 degrees inside, I rotate it once. See, my green is still out, so that means that I only have one negative inside, is my first one. Then if I do it again 180 degrees, I have to rotate it a second time. Now both of them are inside of it. If I rotate it a third time, then my red one's out, but my green one's still in there, so it's only inside of that back number. If I rotate it a fourth time, I get them all out again, so again, I don't have any negatives inside of it, or I'm not negating them. Again, you can still have negatives in the actual coordinate, but you're not changing the coordinate. And then you can also see that they rotate from yx to xy, then yx again, then xy again. They actually rotate each time. For a graphic representation of it, I'm going to give the pre-image coordinates. Point A is at coordinate -2, 3. B is at coordinate 0, 4. And C is at coordinate 1, 1. So I'm going to go ahead and graph that. I have an x and a y and my scale, so I can graph them. -2, +3 is A. B is at 0, 4. And C is at 1, 1. Go ahead and connect coordinates. So what I want to do here is, this time I'm going to give the directions. I want to rotate this figure 90 degrees clockwise. Now, because it says clockwise, that means I have to do the counter equivalent. 90 degrees clockwise really means 270 degrees counterclockwise. We have to do these rules in counterclockwise. So we have to make sure we go here. It says 270 degrees counterclockwise. So in words, we would actually say 270 degrees counterclockwise. The rule for this, so that we can do this, is xy maps to. Since it was the third one, I know I'm going to have yx, I have to flip. It was the third one, so going in once, going in twice, going in a third time, only the back number is negated. So y negative x. So we can actually find our coordinates. So A prime, I flip them first, so I have 3 and a -2. But now I have to negate the back number. So my -2 becomes a +2. My B prime, I flip them first, it becomes a 4 and a 0. Then I negate the back number, which I can't negate 0, so I just keep it as 0. Then C prime, we flip them first, it becomes 1, 1. And we negate the back number, which becomes a -1. Now I have my 3 coordinates, my 3 primes, so I can go and graph them. A prime is at 3, +2. So I have A prime here. B prime is at 4, 0. And C prime is at 1, -1. Now, our center of rotation, because we're using our rules, because we actually had a specific rule, we are going to use the center of rotation of R, and that's at the origin. So this is center of rotation R. Now we do actually want to check to see if this worked. 270 degrees counterclockwise should move 3 different quadrants. So A is right here, so we went 1, 2, 3 quadrants, and it did end in the correct quadrant. B, 1, 2, 3, did move 3, and since it's on the axis, it'll end on an axis, so that actually helps us. And then C, 1, 2, 3, also went 3 quadrants. So then it should be pretty correct that we did do this correctly. Now to prove this, though, we're going to use the property. So to write out the property is that segment AR, so the pre-image coordinate to the center of rotation, should be congruent to A prime R, so the image coordinate to our center of rotation. We should also have BR is congruent to B prime R, so we're going to do the second one. And then we should also have CR is congruent to C prime R. So we can actually prove this, that this happened. So from A to R, so again, we can do the distance formula. Since we're proving congruency, distance formula, or Pythagorean theorem. So Pythagorean theorem would go from A to R, that's going down 1, 2, 3. That's the length of 3. That's the length of 2. Pythagorean theorem. 3 squared plus 2 squared. So 9 plus 4 is 13. So this is the square root of 13. From A prime to R also has 1, 2 length. 1, 2, 3. So we have 2 squared plus 3 squared. 9 plus 4 is 13. So we also have square root of 13. So AR and A prime R is correct. So we have square root of 13 for both of those. If we do B, that goes 1, 2, 3, 4. Since it's on the axis, it's just counting easily. That's 4 spaces away. B prime is also 4 spaces away. So those are congruent as well. Now the last one we have to check C. It's 1 and 1. So 1 squared plus 1 squared is 2. We have the square root of 2 for Pythagorean theorem. Then C prime, 1, 1. That's 1 squared plus 1 squared is 2. So we also have the square root of 2. So since all 3 of them are congruent to their respective parts, that means that this is in fact a rotation. We did this correctly. So we had the square root of 13, 4, and then the square root of 2. So they don't have to, AR and BR do not have to be congruent, but AR and A prime R have to be congruent to each other. So these have to be congruent, these two have to be congruent, and these two have to be congruent. And that shows that this is in fact a rotation. And it was, and since our R was at 0, 0, we can know that that is in fact the center of rotation. And we could change that if we wanted to, but that would take composite transformations.